Hello! Today we are going to continue talking about Aristarchus of Samos, the Greek astronomer who lived between 300 and 200 BC and who figured out some things about the universe that are quite modern from our point of view. So what else did Aristarchus find for us? Well, back to thinking about the universe he had defined so far. Now we've got an Earth. Earth is still the center of the universe at this point. Not sure what he was thinking exactly, but let's just assume he still thought the Earth was the center of the universe, which may have been arguable at the time, but we've got a stationary sun and a rotating Earth, but we still got a problem. The stars are still moving a little bit to the west each day. So Earth rotates around, we're looking at the sun, here's a star. Next day, Earth rotates around, that star has moved here, next day it's moved there. So we've still got the stars moving around the Earth, although the sun is stationary, and we still have the moon, which is closer, moving around the Earth in the opposite direction. So we've still got the stars and the planets all moving independently, and the stationary sun. So Aristarchus thought, well, are the stars moving west in relation to the sun each day, or is it us that is moving? Let's take a look at that for a second. Let's change the model. Now let's put the sun in the middle, the Earth here, and let's put a star over here. Let's put Regulus over there. I like Regulus because I know Regulus goes behind the sun. Although you can't see it, it does go behind the sun. So here's the Earth, there's Regulus, and so we see the sun in front of Regulus. Now what's going to happen? Let's move the Earth. Let's say the Earth is actually going around. Let's put Regulus way out there. The Earth is going around the sun, and so a day later the Earth has moved to here. So now when we look at the sun at midday, we're looking in this direction, aren't we? So day one, we're looking at that direction at midday. The Earth rotates around one time on its axis, revolves around the sun 1 degree, and so what has happened? Now we're looking in this direction. So now we're no longer looking at Regulus. Regulus is now that far. So let's see what happens a day later. The Earth rotates around one time and at the same time revolves around the sun another degree. Now we look at the sun, we're looking in that direction. Regulus has moved even further. Of course, I'm exaggerating this quite a bit, but as we move around the sun, our perspective makes it look like the stars are moving to the west. So now what have we done? We have made two things stationary instead of just one. We had a stationary sun and a moving Earth and a moving moon and moving planets and moving stars. Now we've eliminated one of those moving objects. We have now just one moving object, the Earth, going around the sun. And the reason the stars look like they're moving west each night is because each day we move 1 degree around the sun, which means from our perspective, it looks like the sun is moving east along the sky each day. So now we have a heliocentric solar system. So that's the next thing that Aristarchus gave us, is a heliocentric system. And we're talking about around 280 BC. Are you surprised by this? I was not surprised a whole lot because ancient people weren't that dumb and this stuff isn't that hard to figure out. So now Aristarchus has given us a solar system with a sun in the middle, an Earth going around the sun, and a moon going around the Earth. Because he still accepted that the moon went around the Earth, but the stars are stationary. And the only thing we have left is the planets moving slowly among the stars. Except they do that little funny retrograde thing. Mars does it every 26 months. Jupiter does it every 13 months. Saturn does it every 12 and a half months. So he's figured out a lot of things here, but what we have now is a heliocentric system. Now, there were critics. If the sun is in the middle and the Earth is going around the sun, then what's going to happen to these stars? Let's redraw the Earth without the curly cues of the moon going around it. And just to make it more dramatic, let's put the Earth out here closer to the stars. Okay. So here is the Earth here. We'll put Regulus right there. Okay, so as the Earth goes around, what about here? Well, if we look at the stars in this direction now, they're going to be distorted. It's perspective like when two parallel railroad tracks will seem to converge in the distance. Or if we look at a picture, I can just do that right. Let's see, do I have anything I can hold up? How about this piece of paper I have here? If we look at it this way, it looks rectangular, but what if we look at it at an angle? Now it's looking trapezoidal. That should happen to the stars. Worse yet, if the stars are not the same distance, let's say these stars are all different distances. Just draw little dots all over the place. Now, as we go around the sun, we have stars like right here. Those two stars are in line. But we move around to here, they're no longer in line. In fact, here's a quick little video of an orange tree, and notice as I move the camera back and forth, the relationship between the near oranges and the far oranges shifts. So that's called parallax. And so Aristarchus's detractors said if the Earth were going around the sun, we would see distortions in the shapes of the constellations, at least, or if there are different distances, we would see parallax. Well, Aristarchus had a very simple argument for that. These stars, what are they? They're the same thing as the sun. So there's that bright sun that rules the day. Comes nighttime, the sun is blocked by the Earth, so we see the dark sky and we see these little spots. He said, those are the same as the sun, but they're just incredibly, incredibly far away. So they're very, very tiny and very faint compared to the sun. In fact, they're so far away that what parallax there is so small, we just simply can't see it. So what did Aristarchus give us there? Now we've got a solar system, or a universe, sun in the middle, Earth orbiting the sun, stars incredibly distant. I'm not even going to draw them here. They're just so far away that even though they're just bodies like the sun, they're just faint compared to the sun, and there's no parallax or distortion as we go around the sun because they're just too dang far away. And of course, now we have the moon going around the Earth and the Earth rotating. And so now we are down to stationary body here, stationary stars, one rotating body, not counting the moon, which is rotating around that one. So he gave us that. So now let's take a look at what Aristarchus figured out about the other planets. I'm going to start with Mars because it might be the most dramatic, although you could argue that Venus is, but let's start with Mars. So here's what he had to observe, which we've already talked about before. We have Mars in the eastern sky. We're looking east. The sun has set. Mars is visible. And we just happen to be at just the right time that Mars is at its brightest point. So we have a very, very bright Mars. But what happens? Well, as time goes by, each day as the sun sets, so the sun sets, it gets dark enough to see Mars. And like the stars, Mars is moving to the west. So each night, Mars is a little further to the west. We already talked about that when Mars reaches opposition, which is when it's in the opposite side of the sky as the sun, that it is actually moving the wrong way. So normally the planets move each day just a little bit to the east compared to the stars, but as they're approaching opposition, they turn around and go the wrong way, called retrograde motion, and then after they pass opposition, they turn around and go prograde again. And I'm not going to get into that right now, but I will in a few moments. But we're just going to look at what happens generally. So each night, as it gets dark enough to see Mars, it's a little higher in the sky, and it works its way around the sky until after 10 or 11 months, it's getting pretty close to the sun in the sky, so now it's starting to get over to the west. So the sun has set, it's dark enough to see Mars, and now it's over in the west, getting closer and closer and closer each day to the sun as the stars are moving a little bit to the west. Remember that compared to the sun, the stars move 1 degree to the west each day. Mars is moving almost that fast and also catching up to the sun. But by the time it gets over here, what's happened? Mars is pretty faint. It's around average brightness for the stars. It's not conspicuous at all. You wouldn't even notice it if it didn't have the characteristic red color, and even that doesn't really stand out because it's not really that bright. So what happened? If we go back to our eastern horizon, Mars is at opposition, sun's in the opposite side of the sky. Mars is very bright, but as it works its way west, it gradually gets dimmer and dimmer and dimmer, and when it finally gets to the west, it's pretty faint. It gets very, very dim as it goes toward the sun. So what can we conclude by that? I wish I had a planetarium to show you, but once again, I'll just have to use the board and wave my hands. But what we have here is Mars is climbing over the sky, higher and higher and higher, getting fainter and fainter and fainter, and working its way to the west, to the sun, getting fainter and fainter and fainter, and eventually disappearing into the sun's glare. So what can we conclude by that? Well, let's take a drawing from looking down from the outside. So here's the sun, here's the Earth, and here's Mars, all in a line. So Mars is at opposition, and Mars is very, very bright. So we're on the Earth looking at Mars, and as Mars works its way toward the sun, so now we're looking in this direction, Mars has become fainter. What can we conclude by the fact that Mars has become fainter as it moved in that direction? It must be further away. So did Mars come to about here? No, it must be further away. So let's put it maybe right about there. Now, as Mars gets closer to the sun, let's say when we're looking in this direction, Mars has become even fainter. So is it the same distance? No, it's got to be further away. So let's put Mars over here. Do you see where we're going with this? Now, when Mars is getting closer to the sun, getting ready to disappear into the sun's glare, it's a lot fainter. So we're looking now in this direction, and Mars has become very faint. Is it this far away? No, it's become very faint, so it must be much further away. So what has happened? Mars is doing something like that. And then, of course, it disappears into the sun's glare, comes back in the morning, and does everything in reverse. So what's that telling us? Here is the Earth going around the sun here, and I drew this rather crudely. I'll just fix this up a little bit. I'll use that circle as a guide. It appears that Mars is doing something like this. It looks like Mars is also revolving around the sun, but in an orbit that's further away than the Earth's orbit. So we see Mars very bright here at opposition. It's very close. But when we see it over in this direction, it's fainter, much further away from us. When we see it going into the sun's glare, we see it this direction, much, much fainter. So that is consistent with Mars being in an orbit outside the Earth's orbit. Now, keep in mind that what's really happening here is that the Earth is going around the sun and Mars is going around slower. So as the Earth goes along, Mars falls behind. But what I've done here is I've frozen Earth in place. So we're rotating everything as things go along to keep Earth here. So Mars is here, Earth is there. Everything's moved over to here. Mars hasn't moved quite as much, but what I've done is rotated everything back so that the Earth is here. And then as we go over here and Mars has gone that far, I rotate everything back so that the Earth is here so that we get a much easier view of what's going on. So let's go ahead and erase these. So just keep in mind that that's what I'm doing. I'm rotating everything around so that the Earth stays in the same place and we're watching Mars fall behind as time goes by. And Jupiter, whose orbit is about twice the distance as Mars, I'll just barely be able to fit Jupiter up here. There's Jupiter. There, put some equatorial belts on it. And Jupiter's doing the same thing. When it reaches opposition, it's at its brightest, but as it gets closer to the sun, it gets fainter, but not quite as dramatically. Well, the reason is that the difference between this distance and this opposite distance over here is not as great as the difference between here and there. So Mars gets relatively closer and further away because it's just simply closer. Jupiter being further out doesn't change its percentage of distance as much as Mars, so it doesn't have as dramatic a brightness change. And then you go even further out, way out here, to Saturn, it does the same thing too, but really hardly noticeable. It's not nearly as bright and doesn't get nearly as faint as it goes the other way. So that's consistent with these other planets also revolving around the sun, but just further away. So Jupiter's at its brightest, gets fainter and fainter and fainter. But notice that here we are, what, 1, 2, 3. We're quadrupling the distance between the Earth and Mars, but we're only about doubling the distance between Earth and Jupiter as it goes around, so it doesn't have nearly as much of a brightness change. And then Saturn has even less of a brightness change. So that is all consistent with Mars, Jupiter, and Saturn orbiting outside the Earth's orbit. So that's what Aristarchus said. He said, I believe that Mars, Jupiter, and Saturn are orbiting outside the Earth's orbit. And while we're looking at that, what about that retrograde motion? Do they speed up and slow down? No, they're going the same speed. But in a modern example, if you're driving down the highway and you're catching up to a car that's going slower, when you're well behind it, it looks like it's going forward. But as you pass it, what's it look like? It looks like it is going backwards as you pass it. You're both going forward, but for some time while you are passing it, it appears to be going backwards. And then when it falls behind enough, it looks like you're both going forward again. Aristarchus said that the reason Mars has retrograde motion is we are simply passing it on the celestial highway. So as we approach Mars, it at first appears to be going the same direction, but slower. But as we pass it, it appears to go backwards. So here we are over here, we see Mars, but as we pass it, it appears to go backwards, and over here it appears to be going forward again. So that explains the retrograde motion. So Aristarchus's view of the universe is really simplifying things. Instead of having all these spheres moving at different speeds, we simply have the Earth and Mars and Jupiter and Saturn moving in circles at uniform speed, and all these complicated motions are just perspective. Now let's take a look at Venus and Mercury. Get this out of the way. We're going to put the sun back in the middle, and we're going to put the Earth here, and we're going to do the same thing. We are going to keep rotating our perspective so that the Earth stays at the 12 o'clock position. So let's go ahead and draw a not too terrible circle for the Earth. And now we're going to look at Venus. Well, let's just start when Venus makes its first appearance in the evening sky coming out of the sun's glare. So I'll just draw up here. We're looking to the west. The sun has set, and so there's the sun below the horizon, and here's Venus over there. It's bright, already the third brightest thing in the sky, but it's going to get brighter. And as time goes by, it goes further and further from the sun. And all this time it's getting brighter and brighter. And then finally it gets further and further, and then it turns around and starts going back to the sun. It gets brighter and brighter, gets incredibly bright at one point, and then gets fainter and fainter and fainter and disappears into the sun's glare. And then a week or so later, it pops into the morning sky. So it's gone to the other side of the sun. So now we have to go to the east. And we see before sunrise, there's Venus. Gets brighter and brighter, gets incredibly bright, then starts to get a little fainter, goes up, and then over the weeks works its way down, getting fainter and fainter and fainter and disappearing as it goes into the sun's glare. So what is that consistent with? Well, so it starts out dim and gets very, very bright. I would say it must be getting closer to us. So his argument was that Venus, at first, when we see it, we're looking past the sun and Venus is coming up from behind the sun. And then as it moves away, we're looking in different directions. Well, what's it going to do? Is it going to move in a straight line or whatever? Well, it's getting brighter and brighter as it gets closer and closer to us. And what's happening now is similar to the phases of the moon. If you look at Venus, after it passes its greatest elongation, it's gone as far as it's going to be from the sun, that's its greatest elongation, then it's going to go back to the sun. After that elongation, as we look at it, if you have some binoculars that are 10 power is stretching it, but get close to 15 to 20 power. So you're going to need a little bit of power, more than most binoculars, but you're going to see Venus looks like a crescent, just like the moon. Now, Aristarchus didn't have this, but he had his mind to figure things out. So what happens is Venus suddenly gets faint because here we are seeing Venus front lit by the sun. So we're seeing the bright face of Venus. And we're seeing that most of the way around the orbit. But as we get to around here, I'm going to draw it a little oversized here. The bright face of Venus is, of course, pointing to the sun, just like the moon always does. But see, we're only seeing half of it from this point. And as Venus gets over here, we're pretty much looking at the backside of Venus. So it's going to get fainter. So brighter, 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 fainter, fainter, fainter. So Aristarchus said, I think that Venus is also orbiting the sun, but inside the orbit of the Earth. And that's why it never gets far from the sun, because from our perspective, let me draw the orbit here, it never gets more than 47 degrees from the sun because it stays near the sun. So it goes into the evening sky and back to the sun, goes into the morning sky, back to the sun, taking about 9 months in each part of the sky. So it takes maybe a year and a half, year and 7 months or so. I forgot off the top of my head, but a little more than a year and a half to make one complete cycle from one part of the sky to the other. So once again, Venus in the evening sky goes out and back, and then to the morning sky, out and back and forth between the evening and morning sky. And basically you can count on seeing Venus in the evening sky every other year for about 9 months. And then the morning sky every other year for about 9 months. And so Aristarchus said that's consistent with Venus being in an orbit inside the Earth. And what's Mercury do? Same thing, just not as bright, but doesn't get nearly as far from the sun. So Mercury must be orbiting inside the orbit of Venus. So that is what Aristarchus gave us for the planets. So he put Mercury orbiting close to the sun, Venus next, Earth the third planet, just another planet. So we have the planets and Earth. He said, well, Earth is just another planet. And then, of course, we have Mars. Just for what it's worth, notice that the distances between the sun and these planets up to Mars are about equal, roughly about 30 million miles or whatever kilometers that is each. And then suddenly to Jupiter is about twice the distance as Mars, and so things get way out there. So Mercury, Venus, Earth, Mars, Jupiter, and Saturn, and those were the only planets that were visible in Aristarchus's time. So Aristarchus gave us a pretty good modern view of the universe, about as best as he could considering the tools that he had. So we're talking about 250 to 270 to 80 BC, we had somebody who had it all figured out. Well, like I said before, I don't think he was alone. I think he got his name in print, and so he gets to be famous for it. But as I led you through these thought experiments, you can see it was not a huge cognitive leap to figure these things out. And there were arguments. Does the Earth rotate or do the heavens rotate? And people argued about that. They had arguments for and against. So according to history, Aristarchus's view of the universe was pretty much lost, and everyone believed that the Earth was the center of the universe for 1700 years. Thank you, Mr. Claudius Ptolemy. But as the victors always write the history, I think that this was much more widely accepted in Aristarchus's day than we believe it was now. For one thing, I have seen no evidence that the next person I'm going to talk about, who was Eratosthenes, had any argument against this view of the universe. But I'm sure he had his supporters and his detractors, just like anyone else. And I think that this was much more widely accepted than history tells us that it was. And then the next lesson, we're going to talk about Eratosthenes, who measured the size of the Earth, among other things. And then along came around 100 AD, Claudius Ptolemy, who did not believe in this model of the universe. And because his model was accepted by the major religions of the day, that's what prevailed for about 1500 years, until Copernicus finally came along and straightened us out. Now, I happen to believe that there were people arguing for and against a geocentric and heliocentric universe all through those ages. We just don't hear about them because they were not in control of history. There's even some evidence that Copernicus knew about what Aristarchus had done, although some argue that he could not have. Others say, well, he said he did. And then others say, well, he couldn't have said he did because he couldn't have. Well, whatever. I believe that a lot more people believed this during the so-called Dark Ages than history tells us. But nevertheless, Aristarchus of Samos figured out the universe as we know it. Sun in the middle, planets orbiting the sun. The stars were just other suns, just at a great distance. And that's why today we have statues of Aristarchus, because he had it all figured out more than 2,000 years ago. So the next person we're going to learn about is Eratosthenes, who was the chief librarian at the Library of Alexandria. And we're going to learn how he measured the size of the earth without even leaving the comfort of his library. So until next time, if you found this useful and informative, please give me a thumbs up down below. It really helps the channel and helps other people find these videos. And if you want to study astronomy, you can take my course at vocatomy.net. And if you want to help me make these videos and keep Vocatomy free, you can go to patreon.com/vocatomy and pledge your support. Or for a one-time donation, go to paypal.me/voced, VOCED. As always, a big thank you to my patrons and my donors. I couldn't do this without your support. And thanks to everyone for watching.